Good morning. Today I want to talk to you about magnetism a little bit more. I want to start out with Gauss's law for magnetism. It's just something you might see in a question. So remember, Gauss's law for electricity was Q enclosed over epsilon naught equals EA, and we did tons of stuff with that. Remember, either side of the equation was equal to electric flux. And the electric flux was the amount of electric field going through some imaginary area. Remember the whole imaginary area that we did. So if you had a charged particle and you wanted to know the flux through this circle here, you take the electric field going through here and multiplying it by the area of the circle. And that was how you found the electric flux to use Gauss's law. Well, for magnetism, the same concept works. The Gauss's law for magnetism still talks about magnetic flux, which is BA instead of EA. But here's the deal. If you take a magnet and enclose it with an imaginary circle, any magnetic field lines that go out have to come back in, because unlike an electric field where you can have just a positive charge, a magnetic field, magnetism has to have a north and a south pole. So you can't have just a north pole, so you can't have the flux lines just leaving. They have to leave and come back in. So the bottom line is the magnetic flux is always equal to 0. It's impossible to have just a north pole. So that'll pop up every once in a while. Good thing to know. Okay, today I want to talk about Ampere's law. Maybe this is all going to be reviewed. This is not too difficult, but anyhow, just like a single charge moving perpendicular in a magnetic field feels a force, and we did a lot of that with the mass spectrometer problems. I hope you guys are really comfortable with that. And the force magnetic equals the charge, how fast it's going, and how strong the magnetic field it's in. That will tell you how much it feels a push, right? And use the right-hand rule. Velocity, magnetic field, and your palm of your hand was the push, the direction that it would be pushed. Well, in the same way, a current moving in a magnetic field also feels a force on it. And the formula for that is the similar. Instead of Q, it's I, the current, instead of the charge. Of course, current is a bunch of charges. Instead of velocity, it's the length of the wire in the magnetic field, and then B. I want you to take a moment, maybe after this video, and just verify for yourself, knowing the units for everything, that the units for these equal out to be the same thing. You know, because current and length and coulombs, and this is coulombs per second is current, and meters. And here we have coulombs and meters per second. See how that works out to be the same thing? I guess I just did it for you. All right, anyhow. Okay, why does a current moving in a magnetic field feel a force? Did you ever ask yourself that? Well, the reason is that moving charges and currents create their own magnetic fields. And then their magnetic field, their intrinsic magnetic field that they create, interacts with this external magnetic field. The two magnetic fields interact. So here's the deal. If you take a wire segment, and you wrap your right hand around it, and I can't really do that. Like, let's kind of make that my wire. Wrap your right hand around it. Do you see how on the bottom, at the top, my fingers are coming out, and then on the bottom, my fingers are going in? So this is a new right-hand rule. I call it the gripping the wire right-hand rule. If you point your thumb in the direction of the current of the wire, then your fingers will wrap in the direction of the magnetic field that the wire itself creates. So this is an intrinsic magnetic field. So the wire, this is a part of a long wire, right? And this is the little segment I'm looking at for this formula. No, that's not for this formula, I'm sorry. This is in an external magnetic field. I'm talking about the wire's own magnetic field. So if you take your thumb and point it in the direction of the current, the direction of the magnetic field above the wire will be coming out of the page, and below the wire will be going into the page for a current going to the right. Okay? All right. Now, that leads us to the end here, which is Ampere's law. So if you have a wire, a long wire, I'm just showing a segment of it, in with the current going to the right, and it makes its own magnetic field. And the formula for its magnetic field, this should look sort of familiar to you, is B equals mu naught I over 2 pi r. That is Ampere's law, named after a guy named Ampere. So the deal is this. Because this wire has current moving in it, it generates its own magnetic field. The magnetic field is strongest closest to the wire, and it gets weaker as you move further away from the wire. Thought I had another page in here, but I guess not. It gets weaker as you move away from the wire. So if you want to know some certain distance away from the wire, how strong is the magnetic field due to the wire's own magnetic field, you'd use this formula. Mu naught, like epsilon naught, is a constant. 4 pi times 10 to the minus 7 Tesla meters over amps. I is the current running through the wire. 2 pi, so this is all constant, right? And R is how far you are away from the wire. Okay? And that's Ampere's law. This is pretty easy, what I've just gone over, and I'm going to give you one little easy problem to figure out, and then tomorrow or the next day, we're going to talk about wires interacting with other wires. That's kind of the meatier stuff of this. Okay, here's a problem I want to give you. 2 long current-carrying wires are separated by a distance d. The top wire has a current of 3 amps to the right, and the bottom has a current of 5 amps to the left. What is the net magnetic field at a point P halfway between the wires? And I want to know the direction of the magnetic field there in the middle. Is it into the page or out of the page? And what the magnetic field is. And you can leave it in terms of mu naught and pi if you want, and d. Alrighty. And then maybe you can email me or text me the answer. The other thing I need from you all is I need an email address, maybe from both of you. I have a problem set I want to send you, or maybe I could send it to Iris and she can print it out for you. But either way, will you let me know what would be the best way to get you a document? You guys can just email me, kmusser@aol.com, and I'll send you a little document I want you to work on a problem set. All right, see ya.